අම්මේ ඔයා දාන්නේ 23 213 PDN කියලා නේද? නිරංජි විතරයිනේ.
Good morning. Tumansa Ahmad. Yeah. Those who haven't included the number in the login name, please do that. Yeah, I suppose it is okay. Because time to time, I'll get messages from the computer unit. So Situm Lakshan. Situm Lakshan. The problem is that, some don't respond. I don't know what is happening. Right? Shall we then? Varuna Kahavatta. Varuna Kahavatta. See, problem. Aruna Godamunna. Right. Now imagine I started having kind of an interactive session, talking to some of you individually. Could have been tough time, isn't it? Because you see, nobody's responding. Anyway, right. Okay, I think that's enough. Chintana Abhesekaran.
Sir,
Yeah. Can you add your number to your name?
okay, sir. I just join. I add.
Yeah. Change it to, well, add the number also.
Okay, sir.
Oshadi, Taraka.
Okay, sir.
Yeah. Please add the number. Right. Gamini Ekanayaka. Yeah, that's fine. And then keep all the mics muted. Right. Right. I think under that we went through range, variance, standard deviation, mean absolute deviation, and then quantiles, quartiles, and then, yeah, I think that's what we were discussing. It came up to the point quartile. Yeah. And then in general, we're talking about quantiles. Yeah, the other one is, I think I mentioned, percentiles, quantiles, and then, sorry, quartiles, and then percentiles. The advantage of quantiles in general is that they are not sensitive to outliers. And then we went through methods of finding locations of those quartiles, Q1, Q2, and Q3. I said different approaches are being used. Accordingly, people call it as different definitions. The personal personal concerns, please discuss outside the class time. Thing is that if we start spending time on that, we won't be able to find sufficient time to discuss the subject matter. Okay. So don't drop messages. So the drop messages only with respect to the discussion relevant to what we are discussing at the exact time. Okay. Quantile, so I said that the method method so many different methods are there. I think I mentioned about 9 definitions. So depending on the definition, you find that the value to be sometimes slightly different. Right. So once you have especially Q1 and Q3, then we said we can define a quantity called IQR, which is Q3 minus Q1. So that, like in the case of range, this can be interpreted as IQR is large, higher dispersion is there. If IQR is small, then dispersion is there. And then we had the graphical representation of these quartiles. Q1, Q2, Q3, and on top we have the scale. And then remember in the quiz also what we discussed is that length represents what? The dispersion, not the amount of observations. Right. So that in this case, see, we are in a position to compare the dispersion of observations between Q2 and Q3 relative to dispersion of the observations between Q1 and Q2. So since the length is larger between Q2 and Q3, then we say we have a higher dispersion for that data set compared to the data or the observations between Q1 and Q2. Okay. But now we have a representation of only 50% of the data, isn't it? Because this is 25%, this is 25%. So we have representation of only 50% of the data. Considering only 50% of the data discussing the dispersion may not be that fair, isn't it? I mean, it's not that reasonable. So it's because it's not, well, few observations that we have not considered. Half the data we have not considered. So that people had thought of accommodating representation of the balanced data into this plot. We said this is called box plot. Yeah. Incorporating the representation of the balanced 50%. For that, first we need to define quantity called scale factor. Scale factor is nothing but 1.5 times IQR. That's it. As simple as that. 1.5 times IQR. And then what we do is we mark 1 scale factor. on to both sides, from Q3 as well as from Q1. From Q3 onto the right and then from Q1 onto the left. Mark one scale factor onto two sides of Q1 and Q3. So that we have, as an example, let's say Q1, Q2, Q3. So we mark one scale factor. Okay, everything is according to the scale. One scale factor onto the right of Q3 and then one scale factor onto the left of Q1. This point is called inner fence. Okay, so that we have inner fence from both sides. So that the left-hand side one can be called as left inner fence. And then the right-hand side can be called as right inner fence. And then mark one scale factor from inner fences. Mark one scale factor from inner fences. So from this inner fence, mark another scale factor. And then from left-hand side one also, we mark another one. So the earlier, the point at which we had the termination of the scale factor, we call it as what? The inner fence. So that the second point can be called as opposite of inner is outer fence. So since this is from the right hand side, we can call it right outer fence, and then from the other side, outer fence can be called as left outer fence. And then what we do is we mark the closest observation to the inner fence. Now see, we have the scale on top. So all throughout, we have observations. Around this area also we have observations. Around this area also we have observations. Likewise, everywhere we have observations. And then, as the next step, what we do is, according to the scale, you mark the observation closest to the okay. Mark the observation closest to the inner fence from inside. That is important. From inside. Okay. As an example, let's say we have an observation there, and then we have an observation there. Sorry. We have an observation there. Let's say this is A, this is B. Which one is closer to the inner fence? A or B? B is closer to the inner fence compared to A. But according to the definition here, the observation identified is A. Because from inside means that from center side. Okay. So from both sides, we identify that observation and mark with an asterisk usually. And then what we do is we combine, by the way, this point is labeled as adjacent point. Adjacent point. And then what we do is we connect this adjacent point to the box by a solid line. Combine or the connect adjacent point to the box by a solid line, straight line. This line is called whisker. So we have a left whisker and a right whisker. Correct? Now remember, what we said is that at the beginning, with the box plot, we have a representation of only the middle 50%. There is no representation of the balance 50% in the plot. Now what we are doing is addressing that 50%. Now we have got it. These two whiskers, okay, two whiskers supposed to represent balance 50% of the data. Balance 50%. Well, it is possible that we have the data outside inner fence also. And similarly, outside outer fence also. Observations falling between inner fence and outer fence are usually marked by circles. Usually marked by circles. And observations falling outside the outer fence are marked by solid dots. And then observations falling between inner and outer fences. Inner fence and outer fence. On each side are called mild outliers. Okay. And then observations falling outside the outer fence are called opposite of mild, extreme outliers. Okay, mild outliers, extreme outliers. So that they are extreme outliers. And then this is a mild outlier. Okay. Now we find the plot to be like we have the complete representation. right? Central 50% as well as the balance 50%. In fact, not only balance 50%, we have a clear definition of outliers also. In fact, this is one standard way of identifying outliers. And within the outliers also, we find the classification is there. Now, imagine we have two data sets. Scale and let's say this is the first one and this is the second one. Group 1, Group 2. See how much of a detailed comparison that can be made. We can compare the center, isn't it? And say which one is having higher center, which one is having lower center. And then we can talk about dispersion, overall dispersion, dispersion of the middle 50%, dispersion of the first 25%, dispersion of the last 25%, isn't it? Segment-wise, we can do the comparison, especially with respect to the dispersion. In addition, if outliers are there, they also get marked, so that we can talk about, well, it is possible, not impossible, that one is having outliers, the other one is not having outliers, or the one is having more outliers compared to the other. Likewise, all that can be compared. Okay, so that if you want to compare two sample data, this is one very effective way of making that comparison. Okay. Altogether, this plot is called box and whisker plot. Right. Especially when it comes to ordinal data, if you can remember, yesterday we said that the measure that we used to capture the dispersion or the measure of dispersion is IQR. When it comes to, well, writing an article, you need to first, describe the data that you have collected in your sample. So this is where, remember, I said that we use descriptive statistics. In general, we call them to be descriptive statistics, like sample mean, measure of the center, and then sample variance, that is measure of the dispersion, likewise. But if it is ordinal data we are talking about, suppose now we are dealing with pain scores. Under two groups, we have collected under two conditions. We have collected the pain scores, so that now, well, we need to have summarize the data from the two samples using descriptive statistics, so that if it is ordinal data, pain scores are ordinal data, so that we can use statistics such as, say, median to represent the center, and then IQR to represent the dispersion. Okay. How about qualitative nominal data? Nominal data, sometimes called qualitative data. Okay. Quantitative data, qualitative data. Remember, we're talking about classification of variables, discrete and then continuous, same thing. Discrete, usually we call it the data that we have for discrete variables by qualitative data. Okay, and then for continuous variables, we call quantitative data. So for nominal data, for qualitative data, what kind of measure can be used to describe the dispersion? Variability. One such measure is, now we have come up to what quantiles. Oh, by the way, quartiles we have completed, and then percentiles. Now you see, with quartiles, we can talk about only 3 points, isn't it? Q1, Q2, and Q3. Q1, Q2, and Q3. In order to facilitate identifying more such points that are not sensitive to outliers, we describe percentiles. Now, percentiles are kind of detailed version of quartiles, but quartiles only 3 can be defined. Right. Now, as an example, Q1 is equal to what? We call it 25th percentile. Q1 is 25th percentile. Now, what is Q1? Q1 is a point. Q1 is a point. Q1 is the value of the observation that divides the data set into one to the left 25%, one to the right 75%. So that Q1 is defined as 25th percentile as well. So that when you say 25th percentile means we have 25 observations below that value. And then 75% of the observation, 75% of the observation above that value. Now, as an example, you can tell after getting marks, we make a statement like, you are the 95th percentile in the class. 95th percentile. Meaning, 95% of the students have got marks below you. Only 5% of the students have got marks above you. Okay. 95th percentile. Now you see, in terms of Q1, Q2, Q3, we can talk about only what? Only 3. But by means of percentiles, you can talk about 5th percentile, 10th percentile, 15th, 30th, 45th, 65th, isn't it? 70th, 85th, 95th, 99th, likewise, all that can be discussed. It's not restricted to, but we can go even beyond that and then have measures like 95th percentile minus 5th percentile. Right. 95th percentile P95 minus P5. Advantage is that this is also not sensitive to outliers. Okay. Now we are not talking about just 50%. Now we are talking about what? 90%. So this can be, if you want, call as 90% percentile interval. But percentile range. So earlier we said that interquartile range, that is Q3 and Q1. So this here we have 90% percentile range from P95 to P5. And advantage is that this is also not sensitive to outliers. So this is what is meant by percentile. And then bit of a concern could be there now how to locate these percentiles. Now 25th percentile, 50th percentile, 75th percentile, we have gone through. So using those methods, we can identify then those corresponding percentiles. But see, again, different, as I said, that different definitions, according to those definitions. When it comes to identifying different percentiles, we usually construct step function of proportions. Step function of proportions. Onto this side, proportion, let's say 10%, 20%, 30%, 40%, 60. Likewise, we have the proportions. Onto this side, the values of observations. Values of observations. Okay, so they are maybe 10, 20, 30, 40, 50, 60, 70, likewise, values of the observations. Okay, suppose we have set of values like first one is 12, second one is maybe 18, after that 32, 45, 45, and then 60. Likewise, let's say we have the data. Okay. Now, suppose we have altogether 10 values, n is equal 10. So that up to the value 12, how much of data do we have? How much of data do we have? As a proportion, 0.1. If n is equal 10, then talking about 1 divided by 10, which is 0.1. Okay. And then up to 18, we have 0.2 proportion of data. Okay? So that we mark that information and see 12, value 12, maybe somewhere there. Value 12, we have proportion of 0.1. See, y-axis, the scale is 20, 40, 60, 80, likewise. So that 12 is 0.1 for the 10%. Point 1 is this point. And then next is 18. 18 somewhere there. We have cumulative proportion of 0.2. And then at 18 only, it becomes 0.2. Up to 18, it is only 0.1. So we have it of this form. And next one is 32. 32 is somewhere there. So that up to 32, you have it like this. And then at 32, it goes up to 0.3. Then we have 45. 45. At 45, it goes up to now 0.2, 0.3, 0.5. It goes up to 0.5. Isn't it? Likewise, it carries on. This is what is meant by step function. Okay. Step function. And from this function, we in fact find those percentiles. So as an example, if you want 25th percentile, 25th percentile, then identify the proportion 0.25 and then draw a line perpendicular to 32 we have. Okay, perfect.
The for 12, how it's calculated the proportion 0.1?
Now I said how many observations are there? 10. Okay. So that 12 means see we have organized the data in ascending order. 12 means 12 is just one observation. Up to the value 12, how many observations do we have? Only one, isn't it? 1 out of 10 is 0.1. So up to, and the next one is up to 18. Up to 18, we have 2 observations. 2 divided by 10 is 0.2. Is that clear?
Okay, sir.
Right.
Thank you.
Okay.
Excuse me, sir.
Yeah. Go ahead.
There are two values called 45.
45, that's right.
Yeah. So it comes. How we show them both?
Up to 45, how many observations? Up to 45, how many observations?
2.
Huh?
1.
1,
That's
2, 3, 4, 5. Isn't it?
all. Yeah.
5.
Yeah.
Is that clear?
Yeah.
Right. So that 5 divided by 10 is
0.5.
0.5, that's right. So it's at 0.5. Is that clear?
Yeah.
Right. Okay. Hang on. Right. So when I said this, if we want 25th percentile, then identify now 0.3 is here, 0.25 is somewhere there, so that you construct a line to the curve from the y-axis corresponding to 0.25. Construct a line parallel to x-axis from the y-axis corresponding to 0.25. And then the point at which this line meets the curve, you construct another line towards the x-axis. And this value is Q1. Similarly, if you are interested in 35, draw a line, 35th percentile, like this, and then from the curve, again, you construct a line towards x-axis, and this point is what? P 35, 35th percentile. If you find say, as an example, let's say 30th percentile, 30th percent. So that you identify 0.3, 0.3 is here. You draw a line towards the curve, and you find this line meets the curve exactly at this corner. Exactly at this corner. And you find that it is starting from this point, which is the value, well, in this case, is equivalent to Q1 as well. Is equivalent to Q1 as well. And it goes up to this point, which is, as an example, P35, this value. So then, 30th percentile, so it is starting from this point. So you can see, starting from this point up to this point, or just before this point, you find we are satisfying 30th percentile. Because of that, we take the average of this value and this value. Okay. Suppose this value is this value was how much? 32. This value was 32, and then this value was 45. So that we get the average of 32 plus 45 divided by 77 divided by 2, so that we have 38.5. 38.5 is the 30th percentile. Is that clear? Right. And then one more thing, I think you already noticed that. Now see, as an example, 35th percentile is 45. 35th percentile is 45. How about 40th percentile? Is also 45. Okay. 35th percentile as well as 40th percentile are exactly the value 45. So those are the properties of the percentiles that we calculate from this plot. Then this is how you have, so that you can see sometime you find more than one percentile is satisfied by one observation. Okay, more than one percentile is satisfied by one observation. But of course, if you have many observations, maybe 200, 300, then very rarely you find that several percentiles are satisfied by one observation. Okay. So that find to be like not even one observation corresponds to a percentile. Okay. When you have a lot of observations. Hope it is clear. So this is what is called the method of determining the percentiles using step function of proportions. Okay. A lot of software, in fact, more recent software adapts this method, and then this is what is called definition file. This is what is called definition file. So in case if I use the term definition file, or otherwise in any textbook, this is what is referred to. This step function approach, step function and proportion approach. Right. So that's about determining location of percentiles. mind you, I think as some of you ask questions also is like these proportions are calculated based on individual values. Individual values. See, up to 12, only one observation. So that we have proportion of 0.1 in our example. 18 to 18, we had 2 observations. So that up to 18, cumulative proportion is how much? Cumulative proportion is 0.2. Okay. So individually, we work that out. So that you find as an example, this length is shorter than this length. Not that all have equal length. And then this length, its vertical length, is shorter than this length. So keep that in mind. So all these are possibilities. Okay, right. Let's move on. So that's about quantiles in general, or otherwise quartiles and percentiles. And then, especially when it comes to nominal data, measure of dispersion is called IQV, index of qualitative variation. Index of qualitative variation. IQV is defined as K times 100 square minus summation Pi square divided by K minus 1 times 100 square. Okay, this is how we calculate IQV, where Pi is the percentage of ith category. Percentage of ith category. Let's have an example. Suppose we have 4 categories: A, B, C, D, and maybe as an illustration, 25%, 25%, 25%, 25%. Okay. Let's substitute values. IQV is equal to K. How many categories? Where Pi is the percentage of ith category, and then K is number of categories. Right, now IQV is equal to 100 square minus summation of Pi square is what? Now 25% square is 625. Isn't it? 625, 625, 625. 625 times 4, 2,500. 625, 625, 1,250, double 1,250, 2,500. Divided by K minus 1 is 4 minus 1, and then 100 square. 100 square is how much? 10,000. So 10,000 minus 2,500, and then 3 times 10,000. which is 7,500. 7,500 3 times 10,000. 100 square into 3 into 100 square is 10,000. By the way, IQ is, this is K also we need to have. So how much is K? K is 4. So we have 4 times 7,500 and then 3 times 7,500. So 2,500, sorry, 0, 0, 75. 3 is 4. 3 cancel with this 3, this 4 cancel with this 4. Ended up with what? 1. This particular case ended up with 1. Why specifically I use these values to show that IQV varies between 0 and 1. Between 0 and 1. So that if the value is 1 in sense that is a maximum variability that we can have. Okay, maximum variability that we can have. So that value close to 1 in sense that we are having high dispersion. Value close to 0 means we are having less dispersion. Now you see 4 categories, 25% each, in sense that all are having in equal proportion. All are having in equal proportion. When you say all are having equal proportion, then we have the highest dispersion. We have the highest dispersion. Okay. Now, probably as an example in sense that as homework, change the percentages into A, B, C, D as, let's say, A, 50%. And then B, 30%. And then 80.
The percentage value that you are giving is the frequency, is it so?
Frequency percentage.
Okay, sir.
Percent. Okay.
In a data set, there are 4 types of data and their frequency percentages are given. Is that?
Here,
Okay, sir.
frequency percentages. PI is a percentage of ith category. Can you see that on this? Okay. Now, using this homework is, if the percentages are of this form, of course, some of the percentage have to be equal to how much? 100, isn't it? 100%. Okay, so, right, for this, if this is the case, calculate IQV. That is homework. Compare this value with the value that we calculated. Don't do it now. Do it as homework after class. I know everybody's at home, but do it after the class. This is IQV. Okay. So those are the common measures that we use for the dispersion. Now you can see some are data specific as well. See, IQV is difficult to be computed for the quantitative data. Okay, so IQV is specifically for nominal data. So likewise, we have data specific measures also. Out of all those measures, in statistics, the most common one used is variance, or otherwise the standard deviation. Now, variance and standard deviation, we have one-to-one correspondence. But of course, then they have to be quantitative values, and then for them only you can calculate the variance. For nominal data, obviously, we cannot calculate variance. But so most common value, most common measure uses is variance. However, one of the limitation with variance, we have already discussed one limitation in general. What is it? Sensitive to outliers. Now, apart from that, another limitation of variance is that unit dependent. Unit dependent. Now imagine, probably you will have real world homework also, which I will organize within today itself. But somehow, let's say I ask you to calculate height values, not calculate, consider height values, and imagine I ask everybody to report the height values in centimeters, so that you will have values like 185, 180, 190, 175. Likewise, you have values in 178. Now, values are in centimeters. Suppose the measurements were made in meters, 1.85, 1.8, 1.9, 1.75, 1.78, isn't it? That's how we have. When you say 185, 180, 190, 175 mean relatively large values. And then if you say 1.85, 1.8, 1.9, 1.75, values are small. But we are talking about same set of measurement. Same set of measurement. Now the thing is that if you calculate the variance for the two sets, you will find variance to be different. You will find variance to be different. In general, when the values are large, you find variance also to be high. When the values are large, variance is also large. When the values are small, in general, variance is also small. That's how we find. So imagine then, same height values. One person considering them in centimeters, and then another person considering them in meters. So, person after considering in centimeters might say that, well, look, well, high variability is there because variance is large. And then second person, after considering the measurements in meters, might say that, the variance is small. So that you can see, we have now a bit of an issue, isn't it? We are talking about same height values. Of course, we have the liberty of, taking the measurements in any unit, in any convenient unit. So one person measures in centimeters, another person measures in meters. But the outcome is that after making the measurement in centimeters, person says that high variability is there. Person after making measurements in meters, making the statement of the form, less variability is there.
So excuse me, sir.
Yes.
So in the homework there is only percentage. So how we take the values on to take the summation?
Say that again.
In homework question,
Question. Okay. Yes.
we only have a percentage. So to take the summation, should be their values. I didn't get that point. How we take the summation while calculating the IQE.
Come on.
In the example also you give 625, 625, 625.
25 square is 625.
Yes. And for the homework, we should have values. So only we
Open percentage squares. PI means summation PI square. PI means percentage of ith category. So A percentage is how much? 25. Is that clear? A percentage is 25.
yeah.
B percentage is also 25. 25 square is how much? 25 square is how much? Can you check that with your calculator?
At the moment I didn't have.
It is 625. Okay?
Yeah.
25 square is 625. Is that clear?
Yes.
So that summation pi square is how much? You add all these four values.
Yes.
How much is that? 2,500.
500.
So that you substitute values. 100 square.
So in the example, we need to take the 50 square.
That's right.
50 square, 30 square. Right.
Square
Yeah.
five.
Yes, thank you, sir.
Okay. Right. Yeah, likewise, if you feel that you don't understand anything, don't worry, you just ask. Okay. Thank you for asking questions. Sometimes I find that when I ask a question, nobody's responding. But it's good that at least when you don't understand, asking questions. Right. So you're talking about limitations with variance, the measurement, the summary measure variance. So I said it is unit dependent. And imagine the case, we are comparing the variability of two quantities where the measurements cannot be taken using the same unit. Suppose we are comparing variability of two variables, height and weight. Can we use the same unit? No, we cannot. Now in this example, I said measurements in centimeters and meters. Now we're talking about a situation, say, height of group 1 and then height of group 2. Suppose I am comparing the variability of these two. Variability of these two. It's possible one person has taken the measurement in centimeters, the other person has taken the measurement in meters. Now see the problem that we had. So that problem we can have here too. But then one can ask, okay, well, let's use only one unit so that we can make the comparison. Yeah, that's fine. That's fine. So take the measurements in centimeters for both groups and calculate the variance based on centimeter values. Okay. Yeah, so that we can make a valid comparison. But imagine the case, height and weight. Can we ever have the same unit? Weight is also measured in centimeters? No, that's not possible. That is not possible. Okay. So that you can see there is no way we can use same measurement, same unit, and then calculate the variance and thereby make a valid comparison. So now the question is that how are we going to do that? Correct? So we started the concern with what? The unit dependent. And now we have extended that to what? Comparing the variability of two quantities where the same unit cannot be used to measure both quantities. Right. So how do you handle these two situations? Such a situation, we use the measure CV. Now, which measure is this? Maybe is that okay? 5th, 6th was IQV. 7. CV, which is called coefficient of variation. CV, usually expressed as percentage, calculated as let's say, for example, S divided by Y bar multiplied by 100. Okay. So now we can understand S. What is the unit of S? If the measurements are in centimeters, S will also be in centimeters. If measurements are in centimeters, Y bar will also be centimeters. Isn't it? And multiplied by 100 so that this cancels with this. So that CV is unitless. No unit. Unitless. Because of that, we can make a valid comparison. So that you will find it to be scale independent. So CV is unit independent measure. It is independent of the unit. Right. Let's consider a case where we are comparing variability of rat tails and elephant tails. Rat tails and elephant tails. Rat tails and elephant tails. And then before coming into the comparison, let me put up a question. Difference of 1 centimeter among rat tails, difference of 6, okay, what did I say? Or maybe same here. Difference of 1 inch among rat tails, difference of 6 inches among elephant tails. Which is more noticeable? Suppose we have set of rat tails, and then set of elephant tails. Now I'm talking about one is 1 inch short. Of course, in the whole are not exactly the same. Suppose let's say one is specifically talk about 1 inch short relative to the others. With elephant tails, talking about one is short of like 6 inches or difference of 6 inches. One tail is it's about 6 inches short compared to other tails. Now, question is that out of the two, which one is more noticeable? Is it 1 inch among rat tails or otherwise 6 inches among elephant tails? I suppose, well, 6 inches, of course, larger than 1 inch. 6 inches is larger than 1 inch. But the thing is that elephant tails are in general about, let's say, 4 feet long in general. So then 6 inches, although 6 inches, a length of 6 inches is larger than length of 1 inch, 6 inches among length of 6 inches among elephant tails may not be that noticeable because all elephant tails are relatively large. Rat tails are relatively small. Because of that, you find 1 inch, although 1 inch is relatively small, 1 inch among rat tails is much more noticeable. So that in reality, 1 inch among rat tails represent higher variability compared to 6 inches among elephant tails. But if we go by standard deviation or as variance, all what we are telling is that higher the variance, larger the variance, higher the variability. But the thing, reality is that it's not always the case. Just because variance is large, it doesn't necessarily mean high variability is there. Now see, if the measurements are in earlier also what we said is that, I think it is related to that also. Now height values, if you measure in millimeters, then you will find it to be what? Very high variance, very large variance is there. But it doesn't mean that high variability is there. Exactly. Now here, two different quantities. One is elephant tails, the other one is rat tails. Okay, we are comparing variability of two different quantities. Now you see, by means of variance, what we are telling is variance is comparing the variability. If we do that in using variances, our interpretation is what? We have high variability among elephant tails compared to rat tails. But the thing is that 6 inch and then 1 inch, see, when you compare 1 inch actually among 1 inch among rat tails represent higher variability compared to 6 inches among elephant tails. So you see, that cannot be captured by means of variance. But the measure, CV can capture that. Let's apply that to this example. Now, suppose rat tails standard deviation is 1 inch. Elephant tails standard deviation is 6 inches. Okay. And then suppose mean of rat tails y bar is about 4 inches. And then I said elephant tails is about 4 feet. Y bar 4 feet. Now let's calculate CV. CV for rat is as a percentage. Rat 1 divided by 4 multiplied by 100, which is 25%. And then CV for elephant as a percentage. 4 divided by 4 feet. 4 feet, 48 inches multiplied by 100. 1 over 8, 1 over, so half of 25, that's 12.5. So now you can clearly see rat tails are having high variability compared to elephant tails. See, if you go by the variance or the standard deviation, we said elephant tail 6 and then rat tails only 1. So if you go by the standard deviation, our interpretation is elephant tails are having high variability. But the reality is that rat tails are having high variability. So that can only be captured using CV. So that, remember, whenever you want to compare variability of two different quantities, mean uncomparable quantities, then variance is not appropriate. Better measure is what? CV. And recall the other example I mentioned, comparing variability of height and weight. We can never use the same unit. So the best measure to compare the variability of those two quantities is what? CV. By means of CV only, you can say which one is having higher variability, which one is having less variability. Maybe case like, say, comparing variability of rainfall. Variability of rainfall. Now, if I ask the question,
So it's 4 divided by 48. What is the 48?
48 is the mean. Because what is the formula? What is the formula for CV? S divided by Y bar multiplied by 100. Okay? Is that clear?
Okay, sir.
So S is how much? 4 inches. And then Y bar is how much?
So S is 6 inches.
Huh?
S
Yes,
6 inches, sir.
6 inches.
Elephant.
that's right. 6 inches. 6 inches. And then Y bar is how much?
48.
4 feet. 4 feet in inches.
48 inches.
Okay. Is that clear? Person who asked that question.
Yes, sir. Thank you, sir.
Right. Okay. Right. So I was talking about say a case like comparing the rainfall variability of two different locations. This time, of course, we can measure the rainfall in the same unit, centimeters or inches. The same unit can be used, no issue. But when it comes to comparing the variability of rainfall of two locations, think of the two locations as one is Kandy, the other one is a place like, let's say, Manna. Kandy and Manna. Now, if I ask the question, difference of 2 centimeters of rainfall between 2 consecutive days in Kandy, difference of rainfall of 1 centimeter between 2 consecutive days in Manna, which one do you think you feel more? Difference of 2 inches in Kandy or the difference of 1 inch in Manna? I suppose everybody will say that difference of 1 centimeter Manna is more noticeable. Why? In general, the rainfall is low in that area. In general, the rainfall is low. Because of that, difference of 1 inch, you feel much more compared to difference of 2 centimeters in Kandy, where you find every time it is raining. And the rainfall is so high, I'm talking about relatively, rainfall is so high, you hardly notice the difference of 2 centimeters. But Manna, since the rainfall is very low, difference of 1 centimeter, you feel a lot. Meaning, rainfall difference of 1 centimeter in Manna represents higher variability compared to difference of 2 centimeters in Kandy. But if you go by the variance, that cannot be captured. So to capture that variability, the measure that we had used is what? CV. You see, although rainfall can be measured in the same unit, rainfall in Kandy is not comparable with the rainfall in Manna. Because of that, variance cannot be used to compare the variability. CV is the better measure. Okay, so keep that in mind. Whenever you want to compare variability of two different quantities, uncomparable quantities, even if the same unit can be used, if the two quantities are uncomparable, don't use variance. Use CV. Okay. I suppose, well, at the end of your MSc program, the second semester, the last part, you need to undertake an independent study called directed study. So there you will have to undertake a small scale study, maybe a research, or could even be a survey, whatever. See, so when it comes to dealing with the data, so keep these things in mind. Okay, right. I think I need to get back to the screen. This question is still not clear. The value for k in the numerator is same as the value for k in the denominator. K we were using in both places. K is the number of categories. K is the number of categories. Okay? Hope it is clear. Now, regarding this question. Shehari, is that okay?
Professor, earlier when we were substituting the values, the value for k in the numerator was not substituted. That's why I didn't get the question. Thank you.
Right. Yeah, I think I got that omitted, but I think later I wrote that, didn't I? Okay. Okay. Now only I understood. In the sense, I thought you are now kind of not clear about what is k. Okay, right. Thank you. Okay. Now, in such a time, better to say it, rather than sending a message, because thing is that now you see, now only I'm looking at that message. And then now we find it to be like it's not relevant at all. So best thing is stop me at that time. Then kind of, make the comment. Right. So it's about measures of dispersion. Right. We were talking about summary measures, remember? And what we said is that when it comes to summary measures, we are concerned about two aspects. One is about the center and the other is about the dispersion. Okay. Now imagine, now remember one situation we used to illustrate a real world situation is that you have got a grant and then you have collected the data and then you are making a presentation on the progress. Now see, he said we cannot read all the values, instead we can present the summary. So we had to have a summary for center and summary for the dispersion. And remember, I was telling something like we have collected 1 million values and now you are presenting the summary value of those 1 million values and then summary value of the dispersion. So then how many values have we got now? 2 values. 1 million values reduced to 2 values. One might find the summarization is too much, isn't it? 1 million reduced to 2. Probably summarization is too much. Right. On the other hand, mean is 50. Standard deviation is 10. Let's say as an example. One can have a question of the form where we have most of the values. Is it close to the center? Is it close to the minimum? Is it close to the maximum? Or otherwise evenly dispersed? Or more, less than the mean? And then less, greater than the mean? Different possibilities are there then.
Excuse me, sir. Are you writing on the screen? We can't.
No, I did.
Okay.
I haven't started writing in.
Yeah, okay, sir.
Right. Thanks. Okay. So concern is that where we have more values, where we have less values, maybe we are interested in that information. See, from mean and the variance, we cannot get that information. So that people thought of measures that can be used to have that understanding or have that information. It's about distribution of data. Distribution of data. Measures of distribution of data. What do you mean by distribution? It's like individual location where we have most of the data, as an example. Okay, right. So you can understand with mean and the variance, we cannot have this understanding. This information cannot get revealed by means of mean and the variance. So what measures do we use in day-to-day life? One is frequency table. Frequency table. Where what we do is we categorize data into class intervals. We construct a table, class interval, and the frequency. Class interval and the frequency. As an example, let's say 8, 23, 16, 26, 39, 46, 56, 34. And then 29. Okay. Right. Suppose we thought of class intervals like 0 to less than 10, 10 to less than 20, 20 to less than 30, 30 to less than 40, 40 to less than 50. And then, okay, 50 to less than 60. Frequency 0 to 10, 1. 10 to 20, again 1. And then 20 to 30, we have 23, 26, 29, 3 we have. 30 to 40, 30 to 40, we have 39 and 34, that's 2. 40 to 50, 46, 1. And then more than 50, 50 to 60, 1. 2, 3, 5 to 7, 1, 2, 3, 5, 7, 9. Do we have only, yeah. So to make it 10, let's say we have another one, 21. So that 20 to 30, we have 4. So altogether 10. Okay. First of all, sum of the frequency should be equal to what? The sample size. It should be equal to the sample size. And now, can't we answer that question? What was the question? Where we have more data, where we have less data. If this is the case, we can now clearly say that we have substantially larger number of observations between 20 to 30, followed by 30 to 40. And in other areas, we find few observations. So the answer that we could not make using mean and the variance can be made using this information. What is this? Frequency table. You can clearly say that. Now, around the center, in this particular case, around the center, we find most of the values, and away from the center, we find less values. In fact, so that is the idea. So this is what is meant by frequency table. But we can have additional information like relative frequency. Relative frequency. The usefulness of relative frequency is that imagine somebody asking question frequency of 200. Frequency of 200. Is it a large frequency or small frequency? You cannot give an exact answer, isn't it? If all the other frequencies are like 20s, 40s, 10 and likewise, then 200 is large. If other frequencies are like thousands, then 200 is small frequency. Is it? That's how we have. But relative frequency. What is relative frequency? Relative frequency is frequency divided by the total, n. Where the maximum value possible is 1. See? Maximum value possible is 1. Because of that, whenever we have value close to 1, so as an example in this case, we have 0.1, 0.1, 0.4, 0.2, 0.1 and 0.1. Sum is 1. So that if RF is close to 1, we are talking about high frequency. When RF is close to 0, we are talking about small frequency. Okay. So that convenience we have with relative frequency. And sometimes we consider quantities such as cumulative frequency or cumulative relative frequency. See? Cumulative frequency. Cumulative frequency we discuss by two means. One is less than, the other one is greater than. Less than and greater than. Less than in sense that up to the upper limit of each class interval, number of observations we have altogether. Let me say that again. Up to the upper limit of each class interval, number of observations we have altogether. Or there's a total frequency up to upper limit of each class interval. So the first one, how many up to the upper limit of the first one? Only 1. And then up to the upper limit of second one altogether 2. Upper limit of third one, you have 6. Upper limit of fourth one, 8. Upper limit of the fifth one, 9. Upper limit of the last one, 10. This value should always be equal to this value. Greater than is beyond the lower limit of each class interval. Otherwise, above the lower limit of each class interval, number of observations we have altogether. Now with the first interval, what is the lower limit? 0. Above 0, how many observations do we have altogether? 10. Above 10, how many do we have? 9, because less than 10 we have 1. Above 20, how many do we have altogether? 8. Above 30, how many do we have altogether? 4. Above 40, how many do we have altogether? 2. Above 50, how many do we have altogether? Only 1. That's how we have cumulative frequency. This you can have it for cumulative relative frequency. Less than, greater than. So that we have 0.1, 0.2, 0.6, 0.8, 0.9, and 1. This is 1, 0.9, 0.8, 0.4, 0.2, and 0.1. Okay, likewise.
Sir, can you explain the cumulative frequency greater than again? The 10, 9, 8, 4.
That's right. Okay. That is starting from 0, lower limit. Starting from lower limit, number of observations we have altogether. Now, how many observations are there in our sample? N is equal 10. Isn't it? What is the how many observations do we have in the first interval? Only one. Isn't it? And this value, how much is this value? It is 8. That's why we have included that one between 0 and 10. Now, what I said is, when you look at these values, 10 values, how many values do we have above 0? 10 values, isn't it? Above 0, we have 10 values. So that's why this value is 10. Above 10, how many values are there? Only one value we find below 10. All the other values we find above 10. Because of that, we have 9 here. Greater than. Okay. So you're talking about now greater than. And then about 20, how many do we have? Below 20, we have only 2. So that above 20, we have 8.
Okay, sir.
Exactly. Okay. So with this, especially the cumulative, this is sage. All right, okay. Now this is what we were talking about. If the two data sets are comparable, let's say height values of two parallel classes, you want to compare the variability. That time variance is okay. As long as quantities are comparable. Elephant tails cannot be compared with tails. But elephants in Hambantota area and elephants in Polonnaru area can be compared. They are comparable. That time we can use variance. But if the two quantities are not comparable, then variance cannot be used. In such a case, we need to use CV. Okay.
Sir, excuse me.
Yes. Okay.
Can you explain again cumulative relative frequency greater than part? Column 1, 0.9, 0.8.
Yeah, thing is when you have these values, you divide it by 10. 10 divided by 10 is 1, 9 divided by 10 is 0.9, 8 divided by 0.8. But idea is that went on adding these values. Sorry. So starting from less than is go on adding these values. And then greater than is that go on reducing from 1. Altogether above, how much of relative frequency do we have for the first category? 0.1. how much of relative frequency we have second category, 0.1. Likewise, this is how we have the relative frequencies for each category. And then greater than in the sense that how much of relative frequency we have above the lower limit of each class interval. So that, in fact, all the values we have above the lower limit of the first interval, so that all these get added, which is equal to 1. And then when it comes to second interval, the lower limit is 10. About 10 altogether. We are missing only this one. So that 1 minus 0.1 is 0.9. When it comes to this one, altogether, this part, because beyond 20, this part is how much? 0.4 plus 0.2 plus 0.1 and 0.1, which is 0.8. This one, 0.2, 0.1, 0.1 is 0.4. This one, 0.2, and this one, 0.1. Is that clear?
Yes, sir, clear. Thank you.
Okay, so the usefulness of that one is that you could be interested in up to a specific value, how many values are there altogether? Up to a specific value, how many observations are there altogether? Or then up to a lower limit of a specific interval, how many observations are there altogether? Otherwise, beyond lower limit to upper limit, how many observations are there altogether? So that we can obtain from cumulative frequency. Okay. So location of the observation in detail can be obtained from this strategy, and this is what is called frequency table. So you can call this to be a measure. Now, measure of what? Distribution. Same information, if you want, we can have by means of a graph. By means of graph. Zero, 10, 20, 30, 40, 50, 60. And then frequency. Say 1, 2, 3, 4, likewise. 0 to 10, 1. 10 to 20 also, 1. 20 to 30, 4. 30 to 40, 2. 40 to 50, 1. 50 to 60 also 1. This is called histogram. Exactly the same information we had in the table, but this time by means of a graph. And then probably this could be more efficient, as it says also. Hope everybody has heard the saying, a figure worth 1,000 words, isn't it? A figure worth 1,000 words. Instead of using 1,000 words, you can just include a figure. Thereby, people can understand it more efficient, or otherwise easily get the message effectively compared to reading 1,000 words. Okay. So that taller the rectangle, higher the frequency. That's it. Taller the rectangle, the higher the frequency. Okay. But the theory is that, now you see, very often, width of the interval is, in this case, is how much? Width of the interval. 10, 10, 10. Width is same. Isn't it? Width is same. Because then only you can have a good understanding about where we have more, where we have less. Otherwise, obviously, when the width is high, frequency will also be high. But that is not what we want. We want is where we have more, where we have less. So that as far as possible, we have the width of the intervals to be same. Thing is, sometimes we find, let's say, in the middle, no frequency is there. Then you find it to be like gap is there. Then it is not very attractive, isn't it? You have blanks, because 0 cannot be displayed by a rectangle, isn't it? Right. So to avoid that, sometime what we do is, suppose we did not have what, sorry, say the same one, suppose this one instead of 2 went up to 3, and then next one was 0, and third one was 1. Suppose this is how we had. Okay, so it's not very attractive. So in such a case, what we do is we combine these two. Combine these two. But when we combine these two, we can't have the same height. It is wrong. Isn't it? Wrong representation. In fact, the principle is that area is proportional to the frequency. Area is proportional to the frequency. That's how we have. Okay. So that this has to be then half. Like this. So keep that also in mind. Okay. Because sometimes we construct it that way as well. But the thing is that if the width is same, then you find that height is proportional to the frequency. That's why I said that earlier. Taller the column, higher the frequency. Same thing can be presented for relative frequency also. Instead of frequency, we can have relative frequency on this axis. So that we have like 0.1, 0.2, going up to 0.4, 0.6, 0.8, and 1. Isn't it? And then the class interval. So in this case, shape is going to be exactly the same. Sorry about that. Scale. Say 0.2, 4, 6, 8, and 1. So that 1, 1, 4, 2, 1. Relative frequency. In case if we have relative frequency on the y-axis, and then as the way I said that area is proportional to relative frequency, then the histogram is called density histogram. Density histogram. Okay. What are the two properties or two aspects? Y-axis is relative frequency, and the other one is what? Area is proportional to the relative frequency. There is also usually Rs. Then we call it to be density histogram. Okay. Right. And with frequency also, sometimes we combine the midpoints of each rectangle, midpoint combined. Combined midpoint. And very often this is extended to imaginary one. Think of one more interval, one to the left as well as one to the right. Obviously the frequency is 0 and you combine it to that point. Okay. This is called frequency polygon. Frequency polygon. Okay. And then if you draw a smooth curve, this curve will be smooth one. Smooth one, we call it frequency curve. First one is frequency polygon, second one is frequency curve. Okay, so that's about histogram, and then histogram, and then follow up from the histogram, frequency polygon, then the frequency curve.
Excuse me, sir.
Oh, yes.
Sir, what is the x-axis? How to label it?
You mean this one?
This histogram, the
Class interval.
y-axis ref class.
Class interval.
Okay, thank you, sir.
But in class interval, all what you mark are the limits. 0, 10, 20, 30, 40, 50, 60, likewise. Okay, here also class interval. Well, in the frequency polygon, the reason to extend this curve beyond the rectangles, beyond the x-axis limits, is because then you find total area under the curve. Sorry. Total area in the rectangle total area of the rectangles is equal to total area under the frequency polygon. That is the reason. Okay, up to, well, in the middle, what is missing from one, we capture from the other. Okay, now see. This part is missing, isn't it? But it's captured by this one. Likewise, that is the principle. So that's why we are extending it to, that is to capture this one. We extend it beyond that. So you will find that interesting property, total area of the rectangles is equal to total area under the frequency polygon. And similarly,
Sir,
yeah,
sir, and when the imaginary lines are being extended to the x-axis, at what point should they meet exactly? Within 65 and -5. Is that so?
go on. Now you see, what is the width of the interval? 10.
10.
So that onto the left also you think of a width of 10. Okay, -10. So that midpoint from this to midpoint of this. Is that clear? Like this. Is that clear? Oh.
Yes, sir.
So up to this side also, now you think of imaginary one. Since the width is 10, 60 plus 10 is 70. 70 midpoint is 65. So you combine this to this. Hope it is clear. Right. And then with the density histogram, you should find, since relative frequency is the one, we notice that sum of the relative frequency is how much? Sum of the relative frequency is 1. Because of that, sum of the relative frequency is 1, you will find area of the relative frequencies also to be equal to total area is equal to 1. It is density histogram, total area of the columns is equal to 1. Principle is sum of the relative frequency is how much? Is 1. So what is represented is area in sense that area in sense what? Each one is representing relative frequency. Okay. So that you will find, if you draw it according to the scale, then you will find it to be total area is equal to 1. Right, I think time to have a break. So we'll have break and continue. Oops, what is this? Ah, yes, we shall. That's right. Hope everybody's back. So, shall we start? Yeah, so let the others join. So, most of you are back. Right, so you're talking about histograms at the end. And then as the very last thing, we discuss the density histogram. And then specific properties associated with each of those. Number, histogram, frequency polygon, and then there also we discuss certain properties, and then with the density histogram also we discuss a specific property. Right. First of all, now you see in this histogram, or otherwise class interval, but sorry, in frequency table, we have 6 class intervals. A question could be there that, well, how many class intervals should we have for a frequency table or that's for the histogram? There is no hard and fixed rule. Idea is that, remember, what is the expected information is the distribution of the data. So in order to get that information, we can decide how many class intervals that we are going to have. And then too many class intervals is against like considering each observation separately. Too many class intervals, and each class interval you will have like one observation. So it doesn't serve the purpose. And the other thing is that if we have so many class intervals, can we visualize them in one glance? Now we see 6 intervals. You can easily arrange that in an A4 sheet. 6 class intervals. Yeah, but if you have something like 50, 60 class intervals, one A4 sheet is not enough. And you need to go through several sheets, and then you need to turn from one side to the other. Then only you can get the information. But the thing is that then when you look at the second page, you can't remember everything on the first page, and then when you're getting back to the first page, you can't remember the content in the second page. But if you can have everything in one page, you find it to be like very efficient. So, well, the aim is that in one glance, we should be able to get the required information. And then too few class intervals, that doesn't serve the purpose either. Is it? And it's like only 2 intervals up to halfway is like up to the median and then beyond the median. Well, it's not informative enough. Okay, so it's up to the researcher. There is no hard and fixed rule. But the thing is that we should be able to convey the required information, or that we should be able to get that understanding. As a kind of a thumb rule, we go for like 8 to 12 class intervals. I suppose we can easily accommodate this into one A4 sheet. And then it's neither too few. Neither too many, nor too few. So that is kind of thumb rule that we use for we can have it to like general case 8 to 12. Right, but keep that in mind. There is no any hard and fixed rule. Well, when it comes to histogram, I suppose everybody is familiar with similar tool. Say, 100, 200, 300, likewise, whatever, maybe frequency or otherwise some other measure. Then something like, let's say, oh, yeah. We often use this kind of a tool too when conveying information. How do you call this? Do we call this to be histogram? No, we don't. This is often called bar chart. What is the difference between bar chart and histogram? Now you see, in this bar chart, imagine we have candy one first followed by the gold one. Is it wrong? No, that is also correct. Isn't it? Meaning, in a bar chart, no order in the x-axis. There's no order. But in histogram, there is an order. And as you can see, between goal rectangle and then candy rectangle, there's a gap. There's a gap. But in histogram, no gap. No gap. Meaning, in the histogram, x-axis is continuous. But in the bar chart, x-axis is not continuous. So that's why we had like candy followed by goal is same as goal followed by candy. No problem. But histogram, we cannot have the rectangle for 10 to 20, 10 to 20 after 30 to 40. That's not possible. There's an order as well as there's a continuity in the x-axis. Right, so that's about the bar chart. Right. So with frequency table and histogram, we can have an idea about the distribution of the data. Then, although we can get that information, people came up with the counter argument or otherwise a criticism that once we have the information by means of class interval, we don't have individual information about the data. See, because we have converted data into class intervals. So we don't have individual values anymore. How many between 10 and 20? How many between 20 and 30? How many between 30 and 40 likewise? Okay. As a solution to that limitation, people came up with an idea called third measure, stem and leaf plot. Stem and leaf plot. Stem and leaf plot principle is that if you have value such as 23, 2 is identified as stem and 3 is identified as leaf. so that you can see stem unit is 10 times of the leaf unit. Right? Stem unit is 10 times of leaf unit. Two is identified as stem and the leaf, sorry, 3 is identified as leaf. So the previous data set, remember the example talking about, what was that? Maybe 8, 16, 23, 29, 36, 34, 39, 44, 56, 3, 6, 9, maybe 28. Right. And then what we do is we draw a vertical line. Onto the left of vertical line, we write stem values. Onto the right, we mark or write leaf values. Starting from the lowest value is 8. What is the stem value? 0. And leaf value is 8. What is the next stem value? Stem value, sorry, what is the next value? 16. What is the stem value? 1. Leaf value is 6. Next is what? 23. Stem value is 2. Leaf value is 3. After that, we have 28. Then stem value 2. 2 is already there. Then you write 8. And after that, yeah, 29. Still the stem value is 2 and the leaf value is 9. After that, we have how much? 34. Stem value is 3, leaf value is 4. After 34, we have 36. After 36, we have 39. Same stem value, leaf value is different. After 39, we have 44. 4 and 4. After 44, we have 56. 5, 3, 8. That's right. This is what is called stem and leaf plot. Right. Now, if you wrap those values like this, and imagine rotating this anti-clockwise by 90 degrees. Rotating this anti-clockwise by 90 degrees. What do we get? Histogram. Isn't it? What we get is a histogram. So that all what you get from histogram can be obtained from stem and leaf plot. Nothing is lost. No loss of information. But the thing is, on top of that information, what extra information do we get from stem and leaf plot? The extra information we get is that information on individual observation is on individual observations is preserved. Because complaint was what? We have information only by means of class intervals. Information on individual observation is lost. That was a complaint. But as you can see, this approach, that information is preserved. Right. We get the frequency, Where we have more, where we have less. But meanwhile, we have individual values also. So here you can see that stem values actually represent what? Stem values actually represent class intervals. 0 to less than 10. Is it? 10 is included in the second one. This is 10 to less than 20. 10 is included in the second one. 20 is included in the third one. Okay, that's how we have. So that number of leaf values that we have is equal to what? The frequency of that class interval. So that you find one-to-one correspondence. The biggest advantage is that we know the exact value. Now you see 8, 16, 23, 28. All that information is preserved. That is the advantage. Imagine this value was 29 instead of 28. So that there is no 28. There is no 28. We have 29. And then this is also 29. Also 29. What is the leaf value? 9. 9 is already there. But the thing is, when it comes to leaves, even if values are same, we need to have a separate leaf for each observation. We need to have a separate leaf for each observation. Okay. Stem values won't get repeated. Stem value is appearing only once. Now you see, stem value 0 is appearing only once. Stem value 2 is also appearing only once. Likewise. Okay, but leaf, if you find 2 observations with the same value, then we have to have same leaf value appearing twice. Yeah. The reason is,
Excuse me, sir.
yes.
So when we write the leaf values, we have to write it in ascending order.
Sorry, say that again.
When we write the leaf values, do we have to write it in ascending order?
Oh, yes. Yes. In fact,
Okay, thank you, sir.
that is an advantage of stem and leaf plot, because you find values in ascending order, so that it is easy to identify, let's say, Q1, Q2, Q3, isn't it? Well, I was explaining about this same leaf value appearing more than once. It is because number of leaf values should always be equal to number of leaves should always be equal to n number of observations. Otherwise, if we have the same leaf value, if you have only one leaf value, one leaf per value, then it's possible, especially if you have a tie, or there is 2 observations with the same value, then you find number of leaf values to be not equal to number of observations. So to overcome that, we have it of the form number of leaves to be equal to n. We have to have a separate leaf value for each observation. Separate leaf value for each observation. Suppose we had a large data set. Large data set. If that is the case, then you will find large number of leaf values coming into each stem. This one is very clear, isn't it? Maximum number of leaf values that we have for any stem is 3. So it's very clear. You can easily identify where we have more, where we have less. But imagine there you have about, well, say 15, 20, likewise. Then you find each stem to be like very congested. So many leaf values. So it won't be then very attractive. It won't be that easy to find out the frequency by looking at the leaf values because difficult to count. Now, in this case, you can see 3, 3, 1, 1, likewise. That's how we work. Because we should be able to get the information as quickly as possible. Should not be misleading. I mean, we should not get the wrong information. Should be able to get the correct information quickly. So if you find each stem to be congested, then you find it won't be that attractive. To handle this kind of a situation, we can have stem and leaf plot called double stem and leaf plot. Double stem and leaf plot. Double stem and leaf plot in the sense that you find each stem value appearing more than once. It's like 0, 0, 1 and 1, 2 and 2, 3 and 3, likewise. Okay. So 0, 0 actually implies what? Implies 0 to less than 5, 5 to less than 10, 10 to less than 15, 15 to less than 20, likewise. That's how we are. See, we are having the same width. We are having the same width. This is what is called double stem and leaf plot. So in the previous one, how do you have the values? Okay. Now you see 8, where do you have 8? Between 0 to less than 5 or 5 to 10 is between 5 to 10. So that we will have 8 here. 16 between 10 to 15 or 15 to 20. That is also between 15 to 20. So 16 is coming there. And then 23. 3 is coming between 20 to 20, less than 25. And then the other two, 9 and 9, we have second one. And then 34 we have in the first one. And then 6 and 9 we have in the other one. We have 4 and 4. 5 and 5. So that with 4 and 4, 44 we have in the first one. 56 we have in the second one. Okay. So this is what is called double stem and leaf plot. Mind you, when you have no leaf values, don't have 0, this 0 is written as what? 50. So don't make zeros in a stem and leaf plot. They have a completely different meaning. Okay, keep that in mind. If no observations are there, no leaf values are there, just leave it blank. This is where what I said is that, so find, of course, we go for double stem and leaf plot when we have large number of leaf values falling into each stem, isn't it? So that under normal circumstances, you don't find any blanks, but keep that in mind. Well, if no leaf values falling in, don't write 0. Right. If you still have large number of leaf values falling in, what is the next one? So the previous stem and leaf plot, if you want, you can call it to be single stem and leaf plot. Single stem. One stem value appears only once. Now double stem and leaf value. Each stem value appears 2 times. Okay. What is next one? How about triple stem and leaf value? Then
So when likewise previous when we make the box, so for the empty space, how it's can arrange?
sorry, empty space.
Yeah.
Just leave them empty.
So likewise previous we make the boxes. So when you make the boxes here, so empty space, how it's linked to last to previous?
Well, this means what? 8. This means what? 16. Isn't it? What do you mean by link?
No, sir. She's asking when we make a histogram using stem and leaf plots, there is empty places. I mean, 50, 4, 5. In those areas, how we make histogram?
No,
It,
yeah, I think I understand what we are trying to say is that if there's a blank, what I said is that we combine the adjoining one, isn't it?
no, with the turn anti-clockwise 90 degrees.
Yes, we said it is histogram.
Using the stem and leaf plot, after prepare stem and leaf plot, we turn it 90 degrees anti-clockwise, then we make a histogram.
That's
So
right.
in such case, how we do it for if there is empty leaf number?
Empty.
For, yeah.
In the histogram, there is no frequency.
Yes.
Sure. So it's like, let's say this is 50, 60, 70, 80. 50 to 60, we have value, and then 70 to 80.
Yeah.
After that.
Then it make a bar chart or histogram. There's a gap.
Still,
There's a gap.
No, this gap represent no frequency. But bar chart, it is not relevant, isn't it? There is the bar chart with each column represent separate category.
Yes.
Is in the histogram, if in the middle, if you find no rectangle in sense that frequency is 0.
Yes.
But bar chart, there is nothing like that. Bar chart also, then the thing is that suppose say in the previous one, gold, candy, suppose like Colombo. Let's say this is gold, and then Colombo, suppose it is this much, and then if nothing is there, you can't draw a column or the rectangle. But the thing is that in such a case, you can leave it blank, but theoretically, but the thing is that in a bar chart, when values are there to be presented, only we have them, and then we say that well, the values were found only for gold and Colombo. Now you see in between gold and candy, you have a blank space. isn't it? Now, the in between gold and suppose this is candy. Now, between gold and candy, there's a blank space there. But in histogram, blank space doesn't mean that no frequency.
Yes, because of we have numbers, they are frequent numbers.
And the thing is that this is the category. After that, the category is candy. And there's a space, blank space between the category. But in histogram, there is no such space. Because of that, if there is no rectangle, we take it as what? Zero frequency. Okay. So, bar chart, it's corresponding to the category. So, they are also, if theoretically, if no rectangle in sense that, there is no frequency. Okay.
Yes, sir, it's clear.
Yeah, and then what I thought is that earlier, remember I was telling that sometimes we combine the two class intervals. We combine two class intervals and then, well, have the height to be proportionately, because ultimately what we want is the area is representing the frequency. But that you cannot have in the stem and leaf plot. Okay, because here in the stem and leaf plot, remember we are addressing the issue of what? Individual information. So that if we combine, then the thing is that individual information may not be able to get represented. Right. So talking about we still have large number of leaf values falling in. Then what do we do? Next possible consideration is what? Triple stem. After double, think of triple. If it is triple, how do you have the interval? 0 to less than 3, to 3 to less than 6, 6 to less than 9. Isn't it? That's how we have. So how about then 9 to less than 10? Isn't it? Then you find that it to be a problem. Otherwise, if you have it like 0 to less than 3, 3 to less than 6, 6 to less than 10, then you find this width to be higher compared to these two. The idea is that as far as possible, we have to have what? As far as possible in the sense that unless there's an issue, we have to have the equal width. Width of the interval has to be same. But if it is of this form, then you can see that equal width cannot be provided. Meaning, triple stem and leaf plot is not something possible. What is the next one? 4 stems. 4 stem. If it is 4 stem, can we accommodate equal width? No. 0 to less than 4. And then 4 to less than or equal to 8. After that, we have 8 to less than or equal to, 8 to less than 10. There width is only 2. Cannot provide. So after double, what is the next one? 5 stems. 5 stems can be accommodated 0 to less than 2, 2 to less than 4, 4 to less than 6, 6 to less than 8, 8 to less than 10. Okay. And if you still have large number of values, what do we do? Then separate stem for each value, isn't it? The next possibility is that separate stem value for each value. Like 1, 2, large number of ones are there. Large number of ones are there. A large number of 2's are there. So that we have one stem for value 1, another stem for value 2, like this. So that's about stem and leaf plot. I think with that, we can conclude summary measures. Okay. One homework I would like to give with respect to this summary measure is that real world example. Usually, the example that I give in this kind of a situation is that height values of all the students. Now, what I want is then what I want in the sense that I want everybody to use the height values of all the students and then calculate all the summary measures we have discussed so far. That's the homework. Okay, using height values of students. Compute all the summary measures. Okay, starting from what was that arithmetic mean? Remember? That was the first measure we discussed. Arithmetic mean. Now up to what? Stem and leaf plot. Now the question is how to get these height values. One possibility is that I can ask our system analysis to share a Google sheet so that everybody can write the height values so that everybody can see all those values and using them, and you can easily get them copied into your computer also if you want, or you can easily write them down and then do all necessary calculations. Isn't it? Otherwise, texting and somebody has to compile, isn't it? It's going to be tedious. Let me check with Elaine. Give me a minute.
I wouldn't leave you behind, Dr. Brown. Ready, Case? Yep. Don't leave you behind, Dr. Brown. Ready? Case? Yep. I'll say my see you. First.
Right. Okay, right. So that is sorted out. Okay, yeah. Something I wanted to discuss now has been reminded. Okay, we'll get into that. And I was talking about this Google Sheet. Our system analysis will share Google Sheet, and then that link will also be shared with you all. So everybody can enter the height value into that Google Sheet. Nothing else need to be entered, just the height value. So with that Google Sheet, everybody can see the values. So copy those values and then do the calculations using those values. Since everybody is using the same set of values, everybody should end up with exactly the same value. I don't mind discussing answers, but what you call, don't try to copy it from another person. Okay, do the calculation by yourself, because then, especially when it comes to the examination, you don't get stuck. You know how to do the calculations. Right, and then the message shared here is that regarding accommodating something like decimal values. That's right, that is something I want to discuss. Now see, suppose we have values like, let's start from uh, 120, 240, 230, 410. Likewise. Okay. So as the way we discussed so far, now remember when you say 28, we said 2 is stem and then 8 is leaf. And leaf unit is, as you can see, the what you call the scale location is 1. 2, the unit is what? 10. Isn't it? So that's why I said that stem unit is 10 times of the leaf unit. So if you go by the same arrangement, then as an example, 410 leaf, and then 41 is stem. Then what we will have is, as you can see, starting from see, smallest is then 12. After that, we have 23. After that, 24. So that even if you start from 12, 13, 14, 15, 16, likewise, it goes up to 23, 24, and then it goes up to 41, likewise. And then you can see 12, 0, and then 24, 0. And after that, 23 also 0, 41, 0, likewise. All this space is empty. So that you find it to be like not very attractive. Then. And it's going to be so long as well. Sometimes you find that we cannot accommodate the plot into one A4 sheet. So my find is like plot is extended to several pages or extending it over several pages. So to overcome this, one possibility is that this time we can have this 410 is identified as stem unit to be 100 and then leaf unit to be 10. Stem unit to be 100 and the leaf unit to be 10. So that we will have it of the form 1, 2, 3, 4. And then 1 means what? 100. 1 means 100. And after that we have as the leaf for the first one 2. So 2 means 20. 1 means 100, 2 means 20. So 100 plus 20 is 120. Okay. 2, 3, and 4. 230, 240. And then for 300, no 300 values. And after that we have 410. Thereby, you can make the plot to be much more kind of attractive compared to this one. Okay. Right. Now imagine we have value like let's say 415. 415. What is the stem value? Stem value is 4. It's already there. And then leaf value is now how much? Leaf value is like, now how did we have 3 here? 30 divided by 10. That's why we had 3. Isn't it? So 15, then 15 divided by 10 is 1.5. 1.5. But the thing is that we don't have decimal values in the stem and leaf plot. No decimal values. So you cannot have 1.5. Okay. In fact, all what we have are the truncated values. For 415 also what we will have is 4, the stem, and the leaf is 1. Okay, so that is how it is represented. Obviously, we have a limitation of 410 cannot be distinguished from 415 as an example. Or that's 419, or that's 418 cannot be distinguished. Right? Well, the principle is that, or otherwise count argument is that, when we are talking about that kind of numbers, 420, 425, 485, 684, if you have numbers of that nature, we are not that interested in whether it is exactly 415 or 410. What we want is that around 410, how many values are there? Because of that, we will simply go by 4 and 1. Okay. Right. So that's how we handle, and thereby you can see that we can accommodate large numbers also. Not that every time. Yeah. Quickly, yes.
If you have the observation like 10.6 and 11.6 like that, can we plot into the stem and leaf?
What I'm telling, yes. This is exactly the point. So, next thing is, let me finish this one. So now this is 3-digit number. And it is possible, sometimes we have values to be of the form, let's say, chemical concentration, 0.15, 0.23, 0.09, 0.31 likewise. This is how we have. Let's say, to start with all our decimal values. So in this kind of a situation, we can have 0.1 as the STEM unit and then 0.01 as the leaf unit. So then, it's an example. 1, 2, 3, 4 likewise. So that 0.15 is like 1 and 5. 0.23, 2 and 3, 3 and 1 likewise, and then 0 and 9. Suppose we have 1.2. That is the case if it is like 1.2 as the largest value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Likewise. So we have values 0.31, 0.86, 0.92. Likewise, let's say 1.2 also. So that we can have it this way. 9, 2, 8, 6. Twice. Okay. Meaning, in fact, any number can be accommodated in stem and leaf plot. Thing is, when you are constructing it, as you can see, decimal values are not displayed. I mean, within the plot, we don't mark in terms of decimal values. But the values that we are presenting are kind of decimal values. Let's say 0.23, 0.09, likewise. But the thing is that you don't find the decimal point on the plot itself. So that when you are constructing a plot, it's very important you write what stem unit that you use and what leaf unit that you use. But of course, stem unit has to be 10 times as the leaf unit. Keep that in mind. Okay. So that in principle, or that in general, any value can be accommodated. Okay. Right. So we discussed several aspects. One is that see, relatively large numbers are there, then can have situations where close values cannot be distinguished. Close values cannot be distinguished. Okay, so that situation that we can have, but the thing is that the idea is that we need to have an understanding about where we have more values and where we have less values. That is a principle. So that we can have, although we cannot distinguish something like 219 from 216. Okay. Right. So that's about stem and leaf plot. And then I have given a homework also. So do it by yourself. I want you to understand certain properties of this data by yourself. Otherwise, if I give a data set, you might say that, well, I gave this data set to satisfy the properties that I'm going to discuss. But I don't want that to happen. I want you to understand it by yourself. In fact, the reality in the nature. Now you see, I'm talking about real world data set. Your height values. Not that I'm generating set of values. Okay. With that, I think we can move into the concept of probability. Concept of probability. Usually denoted by P. When do we use the term probability? Day-to-day life. What word do we actually use in day-to-day life? We may not use exactly the word probability, but see, probably, isn't it? Very often we use the word probably in day-to-day.
Chance.
Sorry?
Chance.
No, that's right. No, I didn't ask a similar word, but yeah, that's right. No, what I said is that, say, day-to-day life, we use the word probably. Isn't it? Probably is not a synonym. So probably is the word kind of derived from probability. Probably, when do we use the word probably? When we are not very sure. Isn't it? If you are very sure, we will say that. Yeah. If you think that you can make it, you will say, okay, well, I will be there at this time. Otherwise, you will say that probably I will attend. You are not very sure. So the word probability we use to describe what? Describe something not very certain. When something is uncertain only, we use the word probability to describe that. Right. As one of you said that maybe a close word that we can think of probability is chance. That's right. Isn't it? Chance. Chance is high in the sense that probability is high. Probability is usually a value between 0 and 1. 0 and 1. 0 and 1 is also like imaginary in the sense that 0 means what? Not possible. It's impossible. It's impossible. And then 1 is like absolutely certain. Absolutely certain. But the thing is that real world situation, 0 and 1 is also kind of imaginary sense that now imagine I ask a question, what is the probability of say one specific person in the class, buying a car just after this meeting. Now during the meeting, maybe you have no time, but it's possible sometime, while attending to the meeting, they attend to other things also. Let's say, my question is that, what is the probability of specific person buying a car just after the class? One might say that it is 0. But imagine I ask a person. Tanuja Munasinghe. See, this is the thing. Difficult to get a response. So imagine having an interactive session. It's very difficult. So that's why I always go by a specific person. Cannot ask from a person. Right, anyway, okay. Suppose I ask from a person probability of buying a car just after the class. I bet the answer is kind of 0. But 0, how did we define 0? 0 is less impossible. But is it impossible for a person to buy a car? Just imagine, I have a set of lotteries and I'm going to distribute those lotteries among the students in the class. And if you win, buying a car is nothing. Otherwise, one might say that probability is equal to 0. If I ask why, then they say, well, no sufficient money. But the thing is that If I am going to distribute a lottery, and if you win, buying a car is nothing. In fact, you can buy a car not only for you, you can buy cars for everybody in the class. And so that, is it impossible? Of course, you need to win the lottery. Otherwise, you can't. You need to win. But thing is that not impossible. Any lottery, somebody has to win. So that if you win, buying car is nothing. So that it is impossible. So that there is nothing called impossible. Similarly, having the sunset this afternoon. One might say, yeah, probability is 1, meaning absolutely certain. Absolutely certain. But say, if I reword the question, what is the probability of having a sunset after 1 million years' time? 1 million years' time. Then I bet that nobody wants to answer that question. Isn't it? Because tonight or this evening, everybody might say yes, but nobody would need to answer the questions, and nobody, I bet, nobody would answer to the question, well, probability of having sunset in 1 million years' time. Meaning, even for this evening, there is some uncertainty. If you work out backward, well, in 1 million years' time, you don't want to answer because you are not very sure. Tonight, you started with saying, well, this evening, everybody said, yes, we will have. But 1 million years' time, you cannot insense that even for this evening, there is some uncertainty. There is some uncertainty. So that you can see, in a way, you can argue this 0 and 1 is also like what? Imaginary. But we identify them as kind of boundaries. So probability is always between 0 and 1. Sometime we multiply it by 100. And then express it as a percentage. Yeah, that is also there sometimes. But in general, it's a value between 0 and 1. Before we proceed with probability, let's get certain terms defined. Experiment. Experiment is data generating process. Data generating process. Now, it's an example. You toss a coin. You get an outcome, isn't it? You get an outcome. And then, say, for each toss, you get an outcome. So you are generating data. Any experiment is a data generating process. And then event. Or maybe, I think I need to get back to the screen. So went through an experiment. Then maybe before getting into event, sample space. Sample space is list of possible outcomes from an experiment. List of possible outcomes. Example, tossing a coin. What is the sample space? S, H, and T. Usually denoted as a set. Set. I'm talking about the mathematical concept set. Day-to-day life also we use the word set, same thing. But as you know, in mathematics, we discuss those scientifically. You may not have come that far in the maths course. Yeah, I'm sure you will get exposed to the concept sets in the maths course. Right. This is how we usually denote set. And then see this H and T are called elements. So what are these elements? Elements are the possible outcomes. So this is what is called sample space. Maybe rolling a dice. Rolling a dice. S is equal 1, 2, 3, 4, 5, 6, likewise. Okay. Sometimes you find that the sample space, infinite number of possible values. Sometimes you find large number of values are there. So that you can have, now in this case, fixed number of values are there. So that it could be finite, infinite, and sometimes countably infinite. Finite, like this. Infinite. Infinite. Possible values, say, weight of a nail. Weight of a nail. I mean, could be any value, isn't it? Probably you can have maybe coming from a machine. Suppose you are producing nails, and then suppose you have a target, certain length with certain diameter, likewise. But weights, within the minimum value recorded so far, maximum, you see that, well, every time you find kind of different values, so that any value is possible. Infinite number of possible values are there. And there is no end to that. And then countably infinite. Say that something like number of leaves. You can count 1, 2, 3, 4, likewise, but theoretically it can go up to infinity. So likewise, you can have them into being all these forms. Sample space. Now, next one is event. Event is event is a subset of a sample space. Sample space, list of possible outcomes, and then a subset of that is what is called an event. Example, say event A is observing head tossing the coin. Observing head tossing the coin. See, in the list of possible outcomes, what is the list? H and P. H and P. So, part of that subset is this event. Likewise. When it comes to event, you can have simple event. In the sense that consists of only one outcome. Simple event, sometimes called elementary event. Composite. Several outcomes together. Several outcomes together. Simple in sense that only one outcome. Several outcomes together. Example, say observing 1 or 2 on the dice. Then list of outcomes 1, 2, 3, 4, 5, and 6. So we are referring to both these. More than one outcome. Such an event is called a composite event. Can further be divided. One or 2 can be divided into 1 otherwise we can separate 1 and 2. Now it's 1 or 2 together. That's why it is called composite, but that can be divided into 2. 1 as one event and then 2 as another event. Composite. And joint event. Sometimes we find an outcome satisfy more than one event. Satisfy more than one. Now you see, example, A. Suppose our sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And A would be an odd number. B could be, by the way, joint events. B is number less than 5. Number less than 5. So it's possible, say as an example, number 3 satisfies this as well as this. An outcome satisfy more than one event. So such events are called joint events. Example, now you see, number 3 is an odd number as well as number less than 5. So number 3 is part of A as well as part of B. In fact, these events can easily be represented by means of events can be represented in Venn diagrams. Venn diagrams are extensively used in sets. Okay. So starting from example, A observing 2 on the dice. Okay. So that we know what is S, 1, 2, 3, 4, 5, and 6. And then A is observing 2 on the dice. So A, what kind of event is A? A is a simple event or elementary event. So in terms of Venn diagram, can be represented as this is A, and then inside A, what we have is 2. And other numbers we have outside 1, 3, 4, 5, 6. Same. And then second example, the joint events. Joint events. So if it's a joint event, certain outcomes satisfy both events. Meaning there has to be an overlap between sets. Now let's say this is A and this is B. What was our A? A is an odd number. And then B, number less than 5. Now 1. One. A is odd number. B is number less than 5. 2. 3. 4. Number. Okay. Number less than 5. 1, 2, 3, 4. And then odd numbers 5, 7, 9. Then other numbers 1, 2, 3, 4, 6, 8, 10. Then likewise. So you can see 1 and 3 is common to both. 1 and 3 is common to both. Right. This is denoted as intersection of A and B. Event, joint event. Okay. So the possibility is represented by what? The intersection of two sets. Suppose A is observing head. B is observing tail. So A, can we have an overlap? No, it's not possible to have an overlap. H and T. Since an overlap is not possible, we call such events to be disjoints. Disjoints. Otherwise, mutually exclusive events. Mutually exclusive events. Simple event, composite events, joint events, now mutually exclusive events. One event prevents other events occur. Now, if head is the outcome, tail cannot be the outcome. If tail is the outcome, head cannot be the outcome. Exactly. So such events are called mutually exclusive events. So that in terms of sets, they become disjoints, no overlap. Sets you find completely separate. If one occurs, other cannot occur. Maybe like another example. A is S is 1, 2, going up to 10. And then A is 2, 3, and 4. B is 6, and 7. Is there an overlap? No overlap. So that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we say sample space provides, represent the universal set. Universal set. That is the whole thing. All possible values under the study or consideration. List of all the possibilities. Right, so that you can see these two are also mutually exclusive. And as we can see, now starting from the HNT, if you think of simple events, rolling a dice, oops, simple events like 1, 2, likewise. If 1 occurs, 2 cannot occur. It is like head and tail. If 1 occurs, not only 2, 3 also cannot be occurred. So that you can see all simple events are mutually exclusive. So this is about our definitions, experiment, and then sample space, and then set events. Then classification of probability. First, classical probability. Classical probability. With classical probability, of an event is event A, let's say, is defined as PA, number of events favoring the event. So number of outcomes favoring the event divided by total number of outcomes. Number of outcomes favoring the event divided by total number of outcomes. Example, A, odd number. On the dice. A is odd number on the dice. So PA is what? Number of outcomes favoring the event. How many outcomes favor the event? What are the odd numbers? 1, 3, 5. Out of what? 1, 2, 3, 4, 5, and 6. So the number of outcomes favoring the event is 3 divided by the total number of outcomes, 6, which is equal half. This is what is meant by classical probability. In fact, this was the beginning of the concept of probability, especially when it comes to calculating probability. This was the first concepts developed. It is called classical probability or as mathematical probability. Maybe we have to have a quiz event. Good to have a quiz. So shall we have quiz? Can everybody get ready for the quiz? So don't spend hours and hours. See, now you have another meeting at 1 o'clock. So finish the quiz in 5 minutes. Is everybody ready? See, someone not ready yet, like. Some not around or what? Example, Supuni.
Sir,
I can't see you on the screen. Is your camera on or what? Supuni, is your camera on?
yes, sir.
How come RMCRI Balasuri? Balasuri, not around? If not around, no point being.
Yes, sir.
Okay. Thing is that your camera is not on. We can't see you on the screen. Can everybody have the camera on quickly? We are running out of time. I don't know what is happening here. Hmm. Sijana. Sijana. Hmm. Okay. Right, so let me write the question on the screen. It's a follow-up from classical probability. So let me have that also on the screen so that you can easily give the answer. Let's say A. Let A is the height of a person is equal to 180, 170 centimeters. How much is P? Sorry. How much is PA? Now, 2 past 12.
Sir, where's the data?
Data is this. I'm talking about height of a person. So, definition is given here. That's all. See, just follow this. I said using classical probability. Classical probability, find PA.
Sir, I think each one of them can share the messages to all of us. That means the everyone mode is on.
Thank you. Okay, now it's only to me. Thank you, Ahmad.
Sir, I would like to ask, do you want like a one-line answer, or do you want me to to briefly explain how
Don't explain. Just give me the value.
Okay.
Now, Vitusha, your number is not there along with your name.
I'll change that. I already mentioned that one, sir, with the registration number. I'll check that one, sir.
No, now include your name. Otherwise, when the quiz
Okay, sir.
is coming, I don't know who is it from.
Excuse me,
Yes, who is it?
Prasad. So
Yes.
do we need to mention our name and the registration number in the answer itself?
No, don't write anything. Just send the answer.
Okay.
Because your name and number is there with your name. Sorry, when you send that, that name appears. Don't worry.
Okay. Yes. Okay.
Vitusha, you haven't changed that yet. Okay. Now it is okay. Yeah. I think you need to finish it quickly because otherwise you'll be running out of time to join the other meeting. Has everybody finished sending? Is that all? The thing is that after closing, I cannot accept. Yesterday also, there were about 5 after the time. Right, looks like everybody has submitted. So let me now. Shall I close it now? Right.
Sir, do we need to send the homework also, sir?
We'll talk about that in a minute. Huh? Okay, let me finish with this.
So I sent before, that means I sent a direct message to you. My message is not shown to me. Have you recorded? I don't know.
I hope it is there.
Because earlier it was sent to everyone also, no? But I sent it directly to you.
Okay. Right. Don't send any more. Right. The answer to the question is that, see, definition is number of outcomes favoring the event. Now the last one I cannot accept. Okay. Number of outcomes. Favor in the event divided by total number of outcomes. $170 mean how many possibilities? Means one possibility, isn't it? 170. 171 is also possible. 172 is also possible. Likewise, out of possibilities, 170 is 1. I said equal to 170 is 1. Divided by total number of outcomes. How many possibilities are there for height? 170 is possible. 171 is also possible. 170.5 is also possible. 171.2345 is also possible. Likewise, how many possibilities? We can think of infinite number of possibilities. So that 1 divided by infinity is 0. Just if you, I said just use the classical probability. Number of outcomes, that's 1 divided by total number of outcomes. How many possibilities? Infinite number of possibilities are there. So that 1 divided by infinity is 0. Right. This is the answer to the question. And then we will start from this point. We'll have an interesting discussion, specifically based on this. Any questions or clarifications? Especially you have to join the other meeting. Right, regarding homework, yeah. I give homework for you to kind of make sure you understand the concepts. So you do the homework. If you do homework, when you come to the exam, the meaning, you have understood it. If you can complete the homework inside that, you have understood it. Okay. Usually you don't need to submit. You don't expect to kind of assess. But the thing is that in case if you have an issue, challenge, well, bring that to the next meeting. So you ask the question in the meeting so that we can discuss that. So others also will get benefited out of that. Okay. The thing is that, well, when I give homework, attend to them so that when you come to the examination, you will see that you can answer the question without any problem. So you will have the confidence. So with that confidence, you can easily have, well, 100 out of 100. 100 out of 100 is very common in statistics. If you have understood, you will get full marks. Okay. So shall we then close it for the day? Sorry.
I have a doubt. Excuse me, sir?
Yeah. Yes, Ahmad.
Sir, I think in our quiz, the total number of outcomes, I think it's going to be based on the type of the variable. Is it?
That's right. Now see, dice. Dice, how many possibilities, Ahmad?
6.
That's right. Likewise. That's why I said that sometimes sample space is finite, sometimes it is infinite, sometimes countably infinite, likewise, depending on the experiment. Are you okay?
Okay, sir. Thank you.
So, shall we then close it for the session? No other comments, questions? Let me then close it. Okay.
Sir,
Yeah.
how can we say that the total outcome is infinitive?
That's why I said that. Well, is 170 possible?
Yes.
171? Possible or not?
Yes, sir, possible, but at a time that height should remain constant, isn't it?
Sorry, say that again.
For a person at a time,
Yeah.
his height is same.
Yeah. I'm talking about possibility of that person's height. Probability. Because we haven't seen the person, no. So one question is that if somebody's height. As height, so many possibilities are there. So question is probability of having that person's height to be exactly 170.
Okay, thank you.
Okay. Shall we then?
Yes, sir. I have again the question, sir.
Good. Yes. Looks like everybody's enjoying it. Huh?
Based on the context, that means we are going to consider the height of the person.
Yeah.
So it can be, yes, as a the biological perspective, it can be, we can assume, yes, it is possible to have a 3-meter person, but it can't possible to have more than that.
True.
It can, so the infinity going to be a question mark?
No. The argument is this. Say, for instance, 170 is it possible?
Yes, sure.
180?
Yes, sure.
Between 170 and 180, how many values are there?
Okay, I got it.
Okay, right. Thank you, Muhammad. It's good that, yeah, I can see that. Everybody has to be that enthusiastic. Very good. Shall we then close it for the day? Sorry, for the session? Okay, if no other questions are there, so let me then close it.
Thank you, sir.
Okay, you're welcome.
Thank you, sir.
Thank you, sir. Have a nice day.
Thank you.
Yeah.
Thank you, sir.
Yeah.
Thank you.
See you next week. Yeah. Okay.